Because I do work for the national labs, our business is the science and technology and implementing the policies that federal government sets out. You guys are advocates. We're pleased, that you provide, inputs to the government as to what we should do. That's what the citizens get to do if we right to petition their government. But that's not us. So I'm not going to talk about advocacy about what the government should be doing and stuff, because that's not what the national labs are for. We're there to help when you do get things going with the science and the technology. So, my talk is not this great inspirational type thing. I'm sorry, that's not what I'm here for. I'm not here to advocate. We have some very good people doing advocacy, people taking advantage of the fact that we have a democratic society and we get to advocate for things. And so I'm very pleased when you do that, because it gives me more work, frankly. I'm into doing interesting nuclear things. So my talk is instead on something that we need to do and that we agree on, and is not going to be controversial with any of my lab management or anybody else for me to talk. You will notice that there is a rather dearth of national lab staff here. There's not because national lab staff are not in favor of doing this. It is because, again, this is an advocacy organization that you have, and that's not the purpose of the national laboratories. And so, we do things like radiate your fuel for you on there, do the salt testing. If you want to do the electrolyzer demonstrations on there, those we do those. That's the type of stuff that we support, because it is the science and technology elements on there. People who make decisions are the ones who win elections. That's not us. I'm going to talk about, looking at how you do safety on there, because this is important. Let me tell you, this is a big part of why our reactors are expensive. And there is because, it's only nuclear power that can do a large land denial accidents. I mean, yes, we've done Bhopal. We dropped airplanes out of the sky. Lots of people get killed, a lot more than in any nuclear scenario there. And yet, nuclear power is the one that people remember. How many people remember the various plane accidents? And yet, how many people remember Chernobyl? How many people remember Fukushima and 3 Mile Island and Windscale? They are remembered because of their duration. We have the potential for that large land denial accident. And, in my opinion, we need to make it so that that's not credible, that we're not going to do that again. Because I want to see 10 times as much nuclear energy. I'd like to see 50 times as much nuclear energy as we have today. And if we continue with today's technology and today's method on there, are we going to start seeing these things instead of once every decade or once every 2 decades, once every year? That's just not acceptable. So we need to go ahead and do better than what we've done in the past. Part of the things, I think, is molten salt reactors. Frankly, I've been an advocate of them for a long time, and the fact that they look different. But again, I'm going to be more bureaucratic on this. We can talk offline where I'm not in media presence about my opinions on things. But this isn't my opinions. This is just, let's do safety right. Right here. So we set out, how do we do this? We've known, it was 1946, they did the first Atomic Energy Act, which said, all nuclear power is for the government. Well, in 1954, we decided, well, that's not so much. In the US, it's going to be done in the private sector. And, and the NRC, in this case, it was the AEC until 73, is going to be able to set out whichever standards that protect the minimum health and safety they think is advisable. Again, the Nuclear Regulatory Commission, they provide the rules to implement the legal requirements. Again, reasonable assurance of adequate protection was the rule, back when Edward Teller founded the Advisory Committee on Reactor Safeguards on there. The challenge is, what's reasonable, and who defines that, and how do you go about that? Again, molten salt reactors, every nuclear power plant, same thing. Don't let the stuff out. Hold it in. And that's what containment is on there. Provide adequate cooling. That's one of the things. We have someone who's an advocate of using an accelerator, because you can turn off the heat on there, because you turn things off. But because we got fission for, we have decay heat for quite a while. And so our other thing is, if you don't cool the fuel, eventually bad things will happen. Same thing with control the reactivity. Turns out molten salt reactors make really good prompt burst reactors, so you probably can drop a few dollars into them and without really doing bad things. But most other solid reactors, that's not a good idea. Again, safety functions have to be achieved during normal operations, including anticipated operational occurrences and design basis accidents. We're also looking at beyond design basis. I've been an advocate for a long time of looking at a maximum potential accident, as to essentially take all the energy sources inside containment and dump them all on there. Not very many other reactors would really like to see that. Maybe micro reactors can survive that, but molten salt reactors are kind of distinctive. And the safety functions have to be included throughout the plant life cycle. That's part of those things that when you're taking the plant apart and burning it down, you're probably not going to affect people a long way away. But it's really not a good idea to go ahead and say during the deconstruction phase, affecting your neighbors. Again, efficient and effective safety adequacy is you're just not going to deploy unless we can lower the cost of this. There. Again, you've got really desirable performance and safety characteristics, which we can use to leverage the time, cost and time to doing this. But right now, we're not. Right now, our licensing strategy is based upon the safety characteristics of the large light water reactor. And they're simply because that's the only thing we're deploying on there. The NRC is very responsive. We've got a nice process for going ahead and evaluating their adequate safety. Well, how does low pressure, low chemical potential energy, radionuclide retention in the fuel salt, negative reactivity feedback. All these things impact things, but they're not directly related into the safety adequacy. Again, not saying you don't do the fundamentals. Quality assurance of the things you need to do quality assurance on. Good design, proper construction, adequate maintenance. You always have to do the fundamentals. Again, however, we're not a large light water reactor. We're not a sodium reactor. We have different pieces, and that means we're going to need customized tools and analysis methods. It's not something you're really different. It's just preventing unacceptable releases of materials is the principal safety function. If you look 10 CFR Part 20, for those of you who like the numbers on there, that's the only thing that really puts numbers on there. It says how much radiation you can release to the public there. The challenge is to contain the challenges to containment and the SSCs employed to prevent or release radionuclides are different. Right now we've got rules. We finally got in 2018 to apply functional containment, so we didn't have to apply exactly the same set of containments as a light water reactor, that we can look at all the physics and everything together. Again, low pressure systems, we don't really need these massive containment structures that you have in a high pressure system. Again, the performance requirements for normally salt-wetted credited containment layers are substantially different for things that don't require during normal operations. For example, if you use a guard vessel around your molten salt reactor, it's not normally touching the salt. Well, if you're crediting the guard vessel on there, maybe the guard vessel is made out of 304 stainless. I got a lot of confidence that 304 stainless in 100 hours or so of the accident duration. And then I can use, wasp alloy or something really exotic as my reactor vessel because I wasn't crediting that. That's what functional containment might maybe allow you to do, is to not use credited things as the first thing, is the stuff which is touching your touching the fuel salt. Tritium is going to be a problem. I haven't heard anybody really mention that on there, but tritium is, anything which comes out during normal operations, just because it leaks through. It doesn't leak past, it doesn't have to have holes and stuff. It goes right through. And then your heat exchangers is where your heat exchangers don't work unless you have thin walls. And they also don't work unless they're hot. And so you got to come up with something for trapping tritium. I've got lots of ideas on there, different options for that. But that is sort of one of those major elements that if we don't understand, we're not going to be able to leak large quantities of tritium out. For reasonably good reasons. People with the linear no threshold arguments can make arguments about how much we should be concerned. But living in today's laws, we should be concerned. Again, functional containment, as I said, it's now the law of the land. Individual layers don't have to be leak tight. Matter of fact, you could have no leak-tight layers and just have enough ones to keep, here's 2 orders of magnitude this one, 2 orders of magnitude this one, 2 orders of magnitude this one, and eventually get low enough levels of leakage to say that's okay. Fuel salt is one of the barriers. We just consider, okay, the things come out of that xenon, krypton, some of the iodines come out of this, the tritium comes out of this, but most of the stuff, cesium, strontium, well, if it's born inside the salt, it's not going anywhere. On the other hand, much of the cesium-137 is a daughter product of xenon-137, which has 3.8 minute half-life, and so most of that's money that could be born in the cover gas and wasn't in the fuel salt to start with. Again, normally salt-rated layers might not be code-rated, and therefore you're not crediting them. So again, ASME boiler and pressure vessel code, which is 10 CFR 5055A, is all over the requirements for light water reactors. We may not care because we didn't credit the stuff that's touching the salt. The stuff that's only touching it for a few hours, that's not. I mean, I can do a 304, the low pressure 304 code case is not real hard to do. NRC safety goals, reasonable assurance of adequate protection of the public and the environment. Again, either Part 50 or Part 52. Again, looking at the large light water reactor, there are all those general design criteria. Look at how they were created. Why do they exist? Well, we looked at large light water reactors, and what do we need to protect ourselves against? We did this after 1965 when the Ergen report came out, which said, well, gee, if we actually had an accident where we melted a substantial protection part of the core, we probably can't protect, that's probably not something we can contain. Therefore, we need to figure out how do we make that adequately unlikely that we can still build reactors. And so they came up with a series of, well, if we do this, then we do this, then we do this. We worry about missiles. We worry about containment. We worry about control. We worry about all of the elements that are part of the reactor to prevent accidents and prevent accidents escalation and to mitigate the consequences of accidents. So the existing rules really are quite good. Well, this is where we're sort of highlighting how did we go into 20.2, which is ANS 20.2, which is a design safety rules, the equivalent to Appendix A for light water reactors. And I will have to credit John wherever he's wandered to on there because he provided Vince, which is why this worked. Because Vince Latowski was our secretary. My skill sets are not really well aligned with making sure that we captured all the comments and that we got the voting process to go forward. It took us 8 years to get a consensus standard out for this. It's a lot of work, and John paid Vince for the entire time to have him participate in this, and that we wouldn't. It would have been a lot more harder to do that without that. John, thank you very much. Yeah. Again, advanced reactor design criteria, which they decided we needed to figure out equivalent of the general design criteria, which for light water reactors for the advanced reactors. Molten salt reactors were not popular. They said, well, we're too immature. DOE isn't going to spend the money on doing the advanced reactor design criteria for molten salt reactors. But they did it for sodium and for high temperature gas cooled or modular high temperature gas cooled reactors. Well, we did, and then there's also the probabilistic way of looking at accident prevention and accident endurance, which is really a good way of looking at. I mean, you looked at 3 Mile Island where they said, well, this little part here, this little part here, if this happens and this happens, then you can combine all these things to get a representation of the risk. Well, they did all these things, but they really never looked at how do you do this for a molten salt reactor, simply because it was perceived that we were too immature to be worth investing in. Industry thought different. National labs thought different. Universities thought different. And so we did things through the American Nuclear Society and here as a consensus standard, and that's exactly what we're supposed to do. And again, we're saying, You can use the techniques that we're using today, which is a combination of mitigation and prevention on provide reasonable assurance of adequate protection. But the earliest nuclear power plants really relied upon mitigation. They didn't rely much upon prevention, simply because we didn't know the physics of what was going on that well. And if you don't know what's going on, it's kind of hard to say, well, this is what's going to happen with this accident, and then this is what's going to happen, and then this is what's going to happen. You look at, Dresden 1 or Fermi 1 on here. They had these huge stainless steel vessels that were intended to go ahead and contain things, but they were also only 200 megawatts or so. We have decay heat more than that now on there. So you worry about exactly how did you represent things. Again, the safety adequacy transitioned the accident escalations when it really got too big. Plants that can mitigate with this then really don't need to worry so much about prevention. And that's one of my things, is how do you make things cheap? And I actually have to apologize. I didn't update these on the slides I sent to John. That the top blue box where it says prevention should be prevention and mitigation, which is the deterministic and probabilistic things are, both do prevention and mitigation. So if you look at the probabilistic things, they do the risk triplet. What can go wrong? How likely is it? What are the consequences? And try to build a prevention and mitigation framework. And then you get principal design criteria, which is what the NRC judges you on anyway, which is said this is built this way in there. And you can do that, the reactor class minimum design criteria. And you also have so the other thing is just a pure mitigation approach, which is what's the worst things that can happen, which it gives you containment and distance on there. In the US, we built everything out in Idaho and say there's a long distance away. If we're going to build Indian Point, probably can't do containment. Can't do distance so well. There's way too many people. And the way that's happening is, right now we're trying to put more and more reactors near where people need them, so we don't have the huge transmission issues. Again, the principal design criteria, so just so people know it, it's the way that they establish what are the things that the NRC puts in your check mark. That's what goes into your license, whether it's an ITAC or something, or inspection, testing, analysis, and acceptance criteria, that they actually tell you, well, this is the thing you actually need to do to know that you've met your license condition. So that's eventually what all of these things come out to, is your series of principal design criteria for your plant. Again, understanding and modeling the accident phenomenon really gives you you still have to do the fundamentals, which is what can happen. Well, gee, if I pour salt on the floor and then it will flow down this, or it will react with my concrete. And, it's just the classic sets of good engineering. Just because we're a different reactor class doesn't mean you get out of good engineering practice. Again, we did something like this based upon fundamental safety functions in 2021 at ORNL. Again, while it was DOE sponsored, these are mostly the reactor vendors, the universities, who are involved with that. You still have to do the fundamentals, which is things like, well, gee, what happens if you spill salt on something? Well, we need evidence for that, because the NRC only lives on what's the evidence base you have. We said nothing happened. Well, we're now doing things like dumping uranium chloride and plutonium chloride on the floor in various quantities and watching it flow, getting characteristics. What's the temperature rise when this happens? How much splatters? What comes off in the gas? Oh, you were counting on having a ceiling mounted heat exchanger. Gee, did you get snow on that formed an insulating layer that prevented you from adequately transferring the heat? So there's a lot of evidence from history. Not all of it's quantified. Very little of it's got uncertainty bounds on it. But that is where the DOE is spending its effort right now, is trying to get the separate and integral effects tests that will underlie the basic safety of molten salt reactors. Again, I already talked about this mostly. The regulatory guide 1.232. Again, lots of numbers in my as far as regulations on there, but no equations in my presentation today. But we did not have design-specific, class-specific design criteria for molten salt reactors, and that's what we needed to change, and that's what ANS 20.2 sought to do. As a matter of fact, there's simulated. Okay, frankly, a lot of this, when you're organizing one of these things, basically it looks like the integrated decision-making panel process that's used in 10 CFR 50.69 to create a risk-informed categorization of plants. 8 years. For most of this was at least a meeting a week, a couple hours. It's amazingly tedious work to do standards. If, on the other hand, we have any young people in the audience, almost everybody in the standards is really gray, and they're very worth getting to know, and you could make a real big impact on the future of nuclear energy if you want to get involved in the standards process early in your career. I advocate, strongly to do that. But it will be something that you will spend a lot of time and patiently go through the wording, patiently respond to multiple rounds of voting from people who don't know anything about your technology but have very strong opinions about how your standards should be worded. And patience and consensus building are the key words for any standards process. Again, we can support 10 CFR 50 or 52 based process with this. We're not really good at supporting a Part 53 process yet. We just basically say use the ASME ANS standard for non-LWR PRA. Maybe the next version of this in 5 years will get better at supporting a Part 53 approach, or if we get another version which is based upon Framework B and a maximum containment accident approach, we maybe even have a Part 54. We'll just see where we are. ANS requires every 5 years for you to go over your standards again and see if they need any modifications, and I may still be there, but it may be time for a younger person to decide that they want to do things. It's been a long time on that standard. And that's really all I had for you guys today.
What is your take on Part 53? Where are we with that? And does it do what you think it needs to do?
Well, in my opinion, Part 53 is a viable way of demonstrating adequate safety. I think that it will come out in a reasonable period of time because the Commission on March 4th said, chop off all the extraneous bits and go for sort of the minimum process to go forward. I also think Part 53 is very challenging to apply to new technology because you have to build all your accident models. And if you don't have numbers for your accident models, you end up having to put conservative values in. As soon as you start stacking conservative values after conservative values after conservative values on there, you've made an unaffordable plant. I think Part 53 is very likely to be used heavily for when you have second and third generations of third of kind type plants. It looks very appealing for doing that. I thought Framework B was where a lot of the new plants would go, but a lot of the small plants need something which is a derivative of New Reg 1537, which is how we license non-power reactors. And so I've been advocating to do something which is a maximum containment or maximum potential accident containment strategy, which I'm hoping will be the next thing that the NRC takes up, because Part 53 will help particularly people like NuScale, which has already got a license there, but for people who are looking at doing things which will look looks like something we already have a lot of experience with. We also can do something that looks like this Part 50 or 52 approach, which is what the early licensing documents for terrestrial looks like. Again, my point on a lot of this is not that these processes don't work, but that at the moment there are no reactors in the licensing process. And the reason, in my opinion, for a lot of this is that we're not even going forward is that we've made things too expensive. And if we can't come up with some way of lowering the price of the overall reactor and the overall licensing process, we're not going to win. And I'm hoping that a maximum potential accident way of licensing might lower the costs enough to enable that.
And effectively, we still don't have Part 53, correct?
Yes, it's supposed to be published this fall. The commission said go do this, and the NRC is working feverishly to do that. We sort of have a pretty good outline based upon the votes and the instructions in what's going to be in there, and hopefully it'll be valuable. I mean, Natrium is you look at who's doing things on there, and so first next generation they may be able to do this. So yeah, it's a valuable path forward. Go forward, get this part resolved, and then step forward into the next one. Because right now, I don't think microreactors have a decent path forward. I don't think molten salt reactors have a decent path forward. You can force fit them into the existing frameworks, but the problem with force fitting them is that it costs too much. Not that you don't get adequately safe plants, but we have to lower the price. If we can't lower the price, it doesn't matter for all the other technologies because no one will build them.
Thank you, David. Thank you so much.